Ladies and gentlemen, my name is Patrik Goldschmidt, and this talk is going to discuss the common pitfalls of cybersecurity machine learning and how to design and assess our machine learning model to be practically usable. This is practically a paper reading and knowledge fusion, which was initially presented at our company's knowledge sharing seminar, but I've decided to record it once again for the public to make it accessible for everyone, as I think it might be useful not even for cybersecurity researchers, but for machine learning practitioners and many other people, not only in cybersecurity, who work with machine learning. So if you find this video useful, feel free to leave a comment or write me an email about your opinions. I'll be glad. And so let's get to it. So what is this? As I've discussed, this is a paper reading. Actually, it's quite a paper reading on steroids because I decided to read three papers from top cybersecurity conferences, and since they were very close together, I merged them into one presentation. As we can see, the papers are from 2019, 2022, and 2023, so very fresh perspective onto the machine learning with regards to cybersecurity. And even if you are not doing cybersecurity, you might find this talk useful because the pitfalls presented there are present across multiple domains, and the recommendations can be applicable widely. Of course, every area has its specific pitfalls, specific things that need to be done. But I personally think that these are rather common across multiple fields. So even if you are not doing cybersecurity, you are on the right place. And even if you do cybersecurity, you will hopefully learn something new that you may use for your own research or evaluation of machine learning project. So, okay, something about me. As I've presented myself, my name is Patrik Goldschmidt, and basically I'm in touch with IT since 2012 when I entered high school, and I've studied information and communication technology study program. I finished my master's at Brno University of Technology with the focus on computer networking, cybersecurity, and AI. I worked in CESNET, which is an academic organization, as a student researcher and research and development engineer, primarily focused on computer networking and DDoS mitigation. And since 2021, I worked in a research institute on AI in Bratislava named KINIT, and I'm a research assistant there, and I focus on cybersecurity. And I am also pursuing a PhD at the Brno University of Technology with the focus on data-centric AI for network intrusion detection. So this, what I'm going to talk about, is my topic. I studied it for years, and hopefully I will bring you some interesting insights into the machine learning, cybersecurity, and network intrusion detection fields. Okay, so why you should be there? What's the motivation of this talk? According to Accenture in 2019, 80% of machine learning proof of concepts do not make it into production. This is due to several factors, such as over-optimistic results, which are not achieved in practice, and several issues in data, design, evaluation, or deployment. So these are numerous problems, and we will try to tackle them and to limit the amount of unsuccessful machine learning research or even projects. In cybersecurity, artificial intelligence and machine learning is generally being adopted very slowly because a lot of cybersecurity professionals are skeptic towards the AI. Why? Because AI and machine learning is generally some kind of approximation, And in security, especially in cybersecurity, we need precise, we need accurate results, and we cannot account for mistakes. So we are not often satisfied with approximations, but still the AI is slowly getting adapted into several commercial solutions, and it's very popular research field as well. Okay, another reason is that the practitioners in AI or in cybersecurity cannot really gauge the added value of research works due to missing information, oversimplifications, not sound conclusions, and so on and so on. So what are we going to try to do is to make it easy for them to avoid machine learning pitfalls and to learn to design and evaluate our machine learning model soundly. Let's make our research stand out. Okay, so what are we going to do next? I will present you 10 most common pitfalls in machine learning solutions based on the paper I read. More precisely, do's and don'ts of machine learning in cybersecurity. And we are going to talk about biases, labeling issues, some spurious correlations, issues within evaluation. How are these issues or pitfalls present within the state-of-the-art research? And we will have a case study on code authorship. After discussing these pitfalls, we will take a look on the pragmatic assessment of machine learning models, especially in network intrusion detection. So we will talk about what is a pragmatic assessment, what needs to be done in order to pragmatically assess our network intrusion method, and what's the feasibility of such assessments in practice, and what can we bring to our research projects from this. There won't be any discussion today because this is a recorded talk, but as I said, feel free to write me an email or to drop a comment under the video. And if you manage to stay until the end, I will wish you a beautiful day. Okay, so let's start with 10 most common pitfalls. Pitfall number 1 is a sampling bias. Then we will talk about the inaccuracy in labeling and so on and so on. The important thing is that the pitfalls are present during the whole machine learning workflow of the pipeline. As we can see, this is a pipeline composed of 4 main steps. At the beginning, we got some problem in this talk. It's a security problem, but this practice is applied to basically any other research. So we have a problem. What we need to do, we need to collect the data and label them. In this case, some pitfalls as the sampling bias or labeling inaccuracies might happen. After collecting and labeling our data, we need to design our machine learning system and teach it or use the data to learn it. Yeah. Again, several pitfalls may happen. After designing our system, we need to evaluate it. Finally, we need to deploy it. And then we have a solution. For example, some intrusion detection software. So the pitfalls can happen in every stage of the machine learning workflow, and we are going to slowly look at them one by one, discuss what these pitfalls are, why do they happen, and give you some recommendations, what can you do about them. So, pitfall number 1, as I said, is a sampling bias. What does the sampling bias mean? Basically that the collected data does not sufficiently represent the true data distribution of the underlying security problem. What does it mean? Basically, we collect our samples which are not representative, and our model can learn something else or cannot learn the problem as the whole. We will see on a picture on the next slide. This happens when the research is done without understanding the data. So in most of the data, some bias or some sampling bias will inevitably exist. because it is very hard to sample from the true distribution, especially in cybersecurity. But if we understand the data, it may help us to draw better conclusions or limit this sampling bias impact to almost zero. So what we can try or what we can do to mitigate the bias is by extending the data synthetically, yes, so creating synthetic samples or transfer learning. We can utilize the knowledge from other model or from other dataset. However, especially in computer networking, we should avoid to mix data from two incompatible sources. Why? Computer networks are generally fundamentally different. Even if there are two almost the same networks, but in different geographical locations, or the same networks in the same geographical location, the communication patterns will be inevitably different. Why? There are different users, different protocols, different habits of workers, and so on. And so the patterns of the network are unique, which is, of course, compounded by the internet service provider, or the hardware the network uses, and so on and so on. So if we capture and analyze data from one network, they may be fundamentally different from the other network. And when the attack happens on one network, it may look completely different on the other network. So if we mix data from two incompatible networks, this might not work well and can also create the bias. So we shouldn't mix the data from two incompatible sources, especially in computer networking. And if there are some data limitations, we should discuss them in our paper. Okay, so this is the sampling bias example. Consider this as our true distribution. As you can see, it's some kind of normal Gaussian distribution. Around this point, it's the mean with some standard deviation. Blue is one class and the red is the second class. I think I generated like 500 samples. If we sample, for example, 50 from such a class, we can get something like this. And from the first sight, we see that those data are not totally compatible, that they may come from different distributions. When we design our classifier, for instance, a classification border could go something like this from the true distribution, or if we use discriminative models, or if we use generative models, it will generate something like this or for a class. However, the model would learn something different on this data, and the decision boundary may look like this, so the slope would be different, or the generative model may generate some other representation for the class. So this is why this is what happens when we do have a sampling bias. Our sample on the right does not fully represent the true distribution on the left, creating a bias because our model would learn something different or would not learn the whole class as it is. So the solution to this, yeah, understand the data and know that there may be some bias, or collect more samples, of course, but this cannot be a savior for all situations. So this can be done. And this is another sampling bias example. For instance, now when this is a class 1, class 2, then we get the representation. This should be a representative sample, and this is the biased sample. So the ratio of classes in these two samples is fundamentally different than we would look like. So these are two examples of sampling bias, which is of course undesirable for our problems. The second pitfall, the research in cybersecurity often has, is the inaccuracy of labels, which means that the ground truth labels for classification tasks are often inaccurate, unstable, erroneous, and so they affect the overall performance of a learning-based system. Yeah, machine learning, supervised learning, we need labels, but they are rarely perfect due to noise, due to labeling issues, and this is very complicated in cybersecurity, of course, because it may be hard to tell whether the sample is malicious or not, even for the cybersecurity professional. For example, malware, binary files, or the network traces, and so on and so on. So the labels may be contradictory. One expert might tell you that it's a malware, the second expert would not. This is an example for these malware detectors, for example, VirusTotal or some antivirus software may not be may not give you the same results whether the sample is a malware or not. And of course, the label shift. So what's not malware today might be tomorrow, and so on and so on. So these are two specifics for cybersecurity. What can we do about label inaccuracy? Well, we should verify at least some part, some random sample of false positives our model gives us. And then we can tell if the model is wrong, as we think it is, or the sample that the model processed is wrongly labeled. You may pick, I don't know, 10, 20, 100, depends on your time, false positives via random sampling, and analyze that. If we detect noisy labels, we can get rid of them, but only from the train set, not from the test set, because this creates bias, as we will talk on the next slides. And if we cannot get rid of the noisy labels, or it would be too hard task, we can use more robust models or loss functions, or we can model noise into our training data to make model aware that there is some noise. And yeah, deeper models, more robust models can somehow get through this. So these are two things that can be done. I won't be going to details into these things because that would be out of scope of this talk. But feel free to Google these techniques if you are interested, or anything that I will not explain in detail. Yeah, this is the label inaccuracy example on images. There is a widespread or wide known problem that even images, even the image data, which are easily understandable by humans, contains many wrongly labeled data. As we can see, this on Cipher, this should be frog, but the data set says it's cat, and so on and so on. So the label inaccuracy is present in all datasets, but we as researchers should try to at least gauge the amount of wrongly labeled samples in our data and make some assumptions of it, or how our model is able to deal with these data and so on. So we should at least try to fix it a bit or explain it in our paper. Sorry, I clicked twice. So the problem number 3 is the data snooping. What is the data snooping? Basically, it's a state when our model is trained with the data that is typically not available or shouldn't be available in practice. And it can occur in many ways which are subtle and very hard to identify. So, for example, splitting the data can cause data snooping. There is several types of snooping. For example, test snooping happens when we use test data before the evaluation. For example, for embeddings. Yeah, we do not train with the test data, but we use the data to create some embeddings in our model or for some other pre-processing tasks, which is wrong, of course, but still many research papers do this. A very common, especially in network intrusion detection, my field I work at, is a temporal snooping, when we ignore time dependencies of the data. There are, in some kinds of data, there are temporal dependencies. Network traffic is a typical example. And when we mix those data together from different time periods into our training or into test data, this bias and data snooping may occur, which can create over optimistic results, for instance. And there is a selective snooping, as I've told you on the previous slide, when we cleanse the data based on information that is not available. So we shouldn't cleanse the test data from wrong samples because these information shouldn't be available when we truly test our model. So what can we do with this? We need to strictly separate our train, test, and validation data at the start of the preprocessing. So separate them first, then do the preprocessing. We need to split early during the data collection, and we need to respect our time dependencies that are there. When we use data sets that are not recent, that are older, we should complement them with more recent data sets because on older data sets there could be some issues which are already known, and we as researchers want to achieve that our model achieves the best possible score. So these known issues we tend to fix them, and this shouldn't happen because we shouldn't have those information in practice. So again, we should use some more recent data, and if our data contains time dependencies which are time sensitive, we should avoid cross-validation, as we will talk on the next slide. This is an example from the Pendlebury's paper, but it discusses impact of data snooping, but it is too complicated. So let me simplify it a bit and one more. And at this example, we will discuss what the temporal bias is. So consider each of these square part of the data. In this case, it represents 6 months of data. And the gray square means that the data are not used within the set of, in this case, training set. And the black square means that data are used. And then there is a GV, which is a goodware software or the class 0, and MV, which is a malware software or the class 1. Basically benign and malicious traffic in the context of network intrusion detection, or the class 0 and class 1 in any other machine learning problem in this case. So we have our training and test set, and using the certain parts of the dataset with respect of the time can impact the final results. The results are presented in F-score, and the results are here. And then there are 4 different setups of how we use our data. When we use a tenfold cross-validation, we basically we split the dataset into 10 parts, and we tend to use some parts of the data for testing, then for training, then use a different split, and so on and so on. But what essentially happens is that all the data set from every time period is present in both training and testing. And when this happens, the model would achieve pretty nice results. Yeah, we see 0.91 F-score, which is not bad. But what actually happened? Since we combine data from different time periods, our model got information from the future. So it was taught on a data that were used for testing later. And what this creates is a bias, because newer versions of software may use different APIs or may use different libraries, for example. And so our model could learn differences between these APIs, between these libraries, or the new malware families that come. And even if the malware does not come from the same type, it can come still from the same family, which means that there are some similarities between these classes, and our model can pick on these similarities, which wouldn't be available in practice. So we achieve really optimistic high scores. Then when we use temporal inconsistency like this, that we train on the data that are in the future, and then we test the data that are in the past, again, the score is relatively, well, it's much lower, but it's still relatively good, as we can see. Then there is a temporal inconsistency between goodware and malware windows. What this means, even if the goodware data in training strictly precede the testing data, as we can see, this is 6 months before, and the malware the same, the training data comes before the testing data, score is still relatively good because of the APIs or the libraries and or some biases that may be introduced in this case. So our model wouldn't learn a difference between the malware and a goodware, but it could learn a difference between new functions, new calls, new APIs that were introduced between this time, as we can see. And finally, when we use temporally consistent data, as we can see, goodware and malware comes from the same time period and strictly precedes testing data, the score is much lower. So, what do we take from this? Even if the model achieves high scores, it doesn't need to be realistic if some temporal snooping bias might occur. And finally, if there is temporal consistency, the results could be significantly different. Even if you didn't understood what I've just said on this example, you can check this full example and take a look on that by yourselves in a slower pace, for instance. But the important takeaway is that when we do not respect temporal consistency, we introduce temporal bias and our results might get significantly oversimplified. Okay, so that was the third issue. Fourth issues, or fourth pitfall, corresponds to data collection and labeling. Oh, sorry. This should correspond to system design and learning. I've got it wrong, but never mind. So the spurious correlation corresponds to system design and learning. And what does it set? Spurious correlations are basically artifacts. Yeah. So the artifacts unrelated to the security problem can create shortcut patterns for separating classes. And so the learning model adapts to these artifacts instead of solving the actual task. the same thing as we talked on the previous slides, but those artifacts or the API calls were introduced by the temporal bias or the temporal inconsistency. And in this case, the spurious correlations or the artifacts may exist within the data even without a temporal inconsistency. So these artifacts correlate with the task but are not related to it. What does it mean, or what are the examples? For example, when we consider network intrusion detection, we typically have a packets or a network flow data, and there is some IP address, of course. And our dataset may be formed in such a way that only a certain set of IP addresses performs attacks and does not really perform any benign communication. And then we have another set of IP addresses who do only benign communication. If we fed such data into our model with the IP address, the model could easily learn that these IP addresses are producing attacks. So, okay, when there is some data from this IP address, it would be an attack. Otherwise, it would be benign traffic. And this is completely useless in practice because in practice we have different scale of IP addresses, and so learning whether the IP address is malicious or not wouldn't help in distinguishing the attacks in practice. Also, logo on the image we will see on next slide, and this would cause over-optimistic results and misjudging the practical limitations. So how can we see these spurious correlations? What can we do with that? We should utilize the explanation techniques in our machine learning. So we need to know what our model predicts and why. And of course, we need to understand the data in order to be able to find such artifacts. And then, yeah, see that if what the model predicts makes sense or not. And also, we need to define the objective and advance. And of course, it depends on the solved task and context. In some cases, predicting which IP addresses are malicious and not would be sufficient, yeah, because we defined our objective as such. But in most cases, we want better generalization. So we need to know what do we want to predict and understand how the model makes the predictions. Here is the example, cats with logos. I landed these images from these websites. And as we can see, there is a logo in the right corner in every image. Despite there are only cats, if we feed this data into our model, and every model with and every image with a cat would have this logo, there is some non-negligible chance that our model would learn that the cat depends on this logo and not on the object that is being shown under the image. And then, if our model receives only cats with logos, we would give it image like this of a dog. But there is a logo on the right top, as we can see. Would our model predict a dog or a cat? We don't know, but there is a chance that it may cause the bias due to this logo, and the model would predict the cat. That's the possibility. So this is a visual example we see on the image of what is an artifact and what we do not want to have in our data. But of course, in security, the artifacts may not be visible with our eyes, and such IP addresses or APIs or other artifacts that are not related to the problem should be discovered using the explanation techniques. Fifth problem is a biased parameter selection. And yeah, it again happens during the model learning. And so this is wrong again, but never mind. So the biased parameter selection What it says is the final parameters of a learning-based method are not entirely fixed at the training time. Instead, they directly depend on a test set. Yeah, when this happens, when we screw up our splitting the data into train and test, but we somehow screw it up and we do not use validation set, as we will see on next slide. So what's the description of the problem? We generate different models or different hyperparameters and test it at some data. When we calibrate these hyperparameters on the test data and then used the calibrated model on the test data once again, we introduce a bias because the model wouldn't be able to see and to tune hyperparameters in practice. So it causes data snooping, causes over-optimism, and voila, it causes a problem. So what we can do is to separate validation set for model selection and parameter tuning. And of course, it needs to be realistic. So this is the visualization of the problem. We have a data. They are usually split into train and test. And when we train our data and tune hyperparameters on a test, and then test the tuned model on the test once again, we see that there is some problem because we use the test twice. And it introduces a bias and our optimistic results. What we can do instead, or what we should do instead, yeah, to split our data in three parts: train, validation, test, train the model on train, tune hyperparameters on this validation set, and then finally, after we selected our model, after we fixed our hyperparameters, used it for the test data. This is the very basics of machine learning, but still many research papers struggle with this for some reason, and they introduce a bias and over optimistic results. Okay, we come to the performance evaluation part of the pipeline, and we will discuss sixth pitfall of inappropriate baseline. The statement is that the evaluation is conducted without or with limited baseline methods. And therefore, it is impossible to demonstrate improvements against the state of the art and other mechanisms. What does it mean? That the researchers mostly compare with identical models and do not give enough context to assess the impact of the proposed method. And when you compare only with identical methods, which are mostly overcomplicated or very complex, we increase chance of overfitting. So the recommendations are that we shouldn't compare solely with the complex models, but more simple machine learning models or even non-learning approaches should be considered when we do evaluate our work. Here is an example. The authors compared the state-of-the-art intrusion detection system, Kitsune, an autoencoder ensemble network intrusion detection, against the simple baseline, the box plot method, which is basically giving some threshold values. And as we can see, the simple baseline achieved better score than the state-of-the-art intrusion detection on the dataset the authors used. Why? Because the benign packets, as we can see in blue, are very easily distinguished from malicious packets using only, I think, one feature as the authors used, and these are the malicious packets. So yeah, again, understanding the data, as I've said at the beginning, and compared with other baselines, the assessing improvements of the model could be easier or more sound, for instance. Seventh problem, also in performance evaluation section, are inappropriate performance measures, which means that the chosen performance measures do not usually account for the constraints of the application scenario, such as data imbalance or the need to keep a low false positives rate. So it means that Not all performance metrics, especially in context of security, are suitable for practice. For example, accuracy. Yeah, it's very common metric in machine learning, accuracy, of course. But can we tell the number of true positives or false positives from it? We cannot. Also, the ROCs, receiver operating curve, can obscure our results, and other metrics like macro averaging, micro averaging are known to over or underestimate small classes. So these are the problems with metrics, with measures. And so what we can do, we need to think about the domain. Yeah, we need to know the domain we are proposing the solution for, and we need to choose a metric that is application specific for the practical deployment purposes of the machine learning system. So we need to think about what metrics would the practitioner need, uh, and they typically differ, especially in cybersecurity, from traditional metrics on accuracy and error and so on. So, for instance, interesting metric in network intrusion detection is detection rate, which is basically a recall of class 1 or of a malicious class. So it's not really popular or that popular in general machine learning, but it's rather crucial for the cybersecurity purposes. Yeah, there is an example about how a ROC curve can be misleading in an unbalanced dataset. Here is a 1 to 100 unbalanced class. So there is a one element for 100 elements of the other class. So we do have a model with this ROC curve. We almost perfectly predict this majority class, which can be benign or non-malicious traffic or or software or whatever. But we are totally screwed in predicting the malicious software. But we still receive this very nice ROC curve. But when we plot precision recall curve of the smaller class, the results are not that optimistic as we can see. So choosing a proper metric for the data or for the balance of data we have is really crucial. This doesn't mean that the ROC curve is not great. It's a great indicator, but we need to combine at least with several other precision metrics so we can uh, show the performance of our model better and to make it more interesting for the practitioners, of course. Okay, and then there is the last part of the of our machine learning pipeline. It's a performance evaluation. After we collected the data, we trained the model. We need to evaluate it. Yeah, so one more part, the deployment will come after, sorry. So, but we already trained our model, and now we are evaluating it again. Last slide discussed how a wrong choice of evaluation metric can obscure our results. The base rate fallacy is not about the choice of the metric, but it is about the interpretation of the results. What does it mean? A large class imbalance is ignored when interpreting the performance measures, which leads to an overestimation of performance. Okay, so this class imbalance, which is very typical in network intrusion detection, typical in malware research, is easily misinterpreted or leads to misinterpretation because if a negative class, which is the benign traffic, is predominant, even a very low false positive rates can result in surprisingly high false positives. What does it mean? Then there is an example from the previous figure I've shown it there. When we have 99% of true positives and 100 of false positives ratios. This sound, yeah, nice. The model is doing great. But when we do have an imbalance 1 to 100, what we get from the model is 100 false positives, to 99 true positives, which is not really useful. Yeah. So what we can do, we need to interpret our results slightly better. We need to account for the class imbalance, so we need to use reliable performance indicators, the precision recall metrics and the precision recall curves, as I showed you on the previous slide. And then there are other metrics such as Matthews correlation coefficient, these ROC and AOC metrics, yeah, area under ROC curve, and so on. And also we need to discuss the false positives in relation to the base class in our paper. Yeah. And finally, this is the last part of the machine learning pipeline, is the lab-only evaluation during the deployment and operation. So what the research often does is that this learning-based system is typically evaluated only in laboratory settings without considering the practical limitations of the software or of the proposed mechanism. So researchers often experiment under unrealistic assumptions to demonstrate the super efficacy of their method, but they overstate the impact of the proposed method due to, for instance, a closed world settings, as we will see on the next slide. And what are the recommendations? We should move away from the laboratory settings. We need to approximate the real-world performance as accurately as possible. Yeah, but of course there are things with paper reviewers which may not like that our method achieves a lower performance than the state of the art, of course, and or that in baseline. But when we, I believe, sufficiently discuss that this is the real world, the real world performance could be much more similar to our results than the current over-optimistic results, then I think the reviewers would like the idea. But yeah, we need to discuss why our results from approximation of real-world environments could be slightly lesser than the existing research. We should focus on open world settings. Again, I will discuss closed world and open world on the next slide. We need to, or we should consider little available training data. So only 100 samples, 1000 samples, and so on. So what happens when there is not enough data for training? We should discuss or consider the spatial and temporal relations of the data. So temporal dependencies, as we talked, and the spatial dependencies basically discuss the class ratios between the reality and our laboratory environments. So our goal is to achieve as realistic spatial relations, so the ratio of classes in reality and in our data, and temporal relations should be respected. Yes, so we shouldn't have data available from the future, of course. And we should consider runtime and storage, which means that we should specify into our paper how long does the method take, how many gigabytes of RAM do we need, and so on, which is really important to discuss for the practical usage of the method. So I promised you closed versus open world setups or illustrations. So the closed world scenarios means that there are same classes in a test set. We see red, green, and blue as in the train set. So the model only receives the same classes during the testing as it was trained on. However, open world scenario, which is much more realistic in practice, consider a new type of attack that emerges that our model was not trained on, or a new type of protocol to analyze, which again our model wasn't trained on because it didn't exist in the past. So our model is trained on these three classes, but in testing it could get other classes like this purple and yellow star. And there's open world learning, machine learning problem. You can check several papers on that, on how to handle such problems when our model receives data from fundamentally different classes than it's seen before. Of course, in our case of detection of attacks or in cybersecurity, we should be able to discuss or to decide whether the sample is benign or malicious and so on. And this could be achieved, of course, with anomaly detection. So is the new sample looking anomalous? Does it provide any anomalous behavior or not? And if not, then yeah, it probably could be benign or it could be non-malicious. And if it has some malicious behavior, that we can tell with some precision that yeah, this sample looks malicious, although we don't know what's the precise attack that is happening. Yeah, so this is another consideration. And the very last pitfall during the deployment and operation of the method is inappropriate threat model, which means that the security of the machine learning is not considered. And it exposes a system to a variety of attacks, such as poisoning and evasion. What does it mean? The machine learning systems, especially in cybersecurity, operate in hostile environments. The goal of attackers is to infect the system or fool the protection, the security mechanism. And so researchers should consider these problems or these possible attackers during the design phase. So they should count or they should think about how can the model be defeated or somehow fooled using several adversarial techniques. There is adversarial learning subfield in machine learning, but yeah, in cybersecurity, the adversarial learning should be considered by design. Yeah, so that's it. And our recommendations, or the recommendations of the paper creators, is to design and evaluate the model with respect to adversarial adversarial environment, and to assume adaptive adversary, which is targeting proposed system and exploiting weaknesses for evasion of manipulation. As we know, there is adversarial machine learning in images when we can change like one pixel or make the image look totally the same for humans, but the model totally fails distinguishing the image class and so on. And this is really similar in machine learning for cybersecurity. We need to think how the cybersecurity machine learning model could be fooled with the data, what the attacker can do to fool the system, and so on and so on. This again requires the domain expertise from the researchers, which are proposing the method, and that's it. It should be proposed during all stages of machine learning attacks. So how can our data be poisoned? How can our model be, I don't know, trained in adversarial manner? How can the attacker influence the evaluation of a model? And how, what we can do or what the attacker can do during the model deployment. Yeah. And of course, white box attacks, we'll be talk about them briefly in the next slides, mean that the attacker will know the full information about the model. Yeah, so those are white box attacks. So attacker would know what the model or what machine learning model does the security system use, what are the hyperparameters even, and so on and so on. Yeah. So those were 10 most common pitfalls of machine learning research in cybersecurity during all 4 stages of machine learning workflow. Then the attackers did a prevalence analysis from 30 papers from top 4 A-star cybersecurity conferences. And as we can see, these pitfalls are present in almost or in every research, and the sampling bias, as I've been talking at the beginning, the data snooping is also very popular or very common, and then this lab-only evaluation and threat model are not considered, are considered only partially. Yeah, so this is the state of the art prevalence of the pitfalls discussed here. Okay, so then the authors did a case study. Give me a sec. Then the authors did a case study of how these pitfalls affect the machine learning research in practice. So they focused on three things, I believe. For our example, I focused on the problem of source code author attribution, or the authorship attribution problem, which is basically an identification of the developer based on the source code problem. Yeah, so there are some programming habits of every programmer characterized by stylistic patterns, and what we can do, or what the model can do, is to pick up on these stylistic patterns and determine who is the author of the code, for example, for plagiarism detection or other use cases. And the very popular dataset used in this domain is based on a Google Code Jam competition, where the participants solve the same challenges, and it is good because the model can learn separate stylistic patterns of the authors rather than overfitting to different challenges. So yeah, this is very fine. But what is the issue with this kind of data? That the most participants, of course due to time reasons, copy the same code across multiple challenges as templates. And so these templates are often not used to solve the challenges, but they are just unused or dead code inside the solutions, which really deviates from the real world examples, because they create possible artifacts. Yeah, the code is there, but not used. So the model could pick up on these parts of a code instead of doing really stylistic patterns that we want. So the authors analyzed two studies, and this TB is the original study. As we can see, it is it's accuracy, and the original study, this is around 90 something percent. There is also 90 or 80 something percent, and the authors of this case study did two things. The first, in T1, they dropped the unused code only from the test set. Yeah, this is T1. So the data or the models were trained on the same data, but the unused code or the dead code were dropped from the test set. And as we can see, the accuracy dropped rapidly to around 40 or 50% in both cases. Then the authors removed the dead code or the unused code even from the train set and retrained and re-evaluated. The accuracy jumped back a little, but still it is worse than the original study. So again, this is an example of how in this case, spurious correlations can cause over-optimistic results in real cybersecurity research produced or published on top conferences. So that was it. That was the first part of the 10 most common pitfalls. And the second part will focus on how do we assess our machine learning model pragmatically. It will be focused on network intrusion detection, but I believe the principles could be again applied to many other domains. So how do we assess, or what is the pragmatic assessment? From the very start, let's just discuss this nicely theoretical slide, which gives us what is the value of machine learning security solution. So the value of the machine learning security solution is kind of based on efficiency or on effectiveness. And we want it yields a high detection rate with a very few false alarm. And in just a theoretical manner, this value is influenced by many factors like data preprocessing, data availability, of course, the size and sample, because the data have their cost. Then the system infrastructure. So what is the machine learning pipeline? What predictions do we make, binary, multi-class, and so on? What hardware do we have? And of course, value is influenced by the unpredictability. So this is just a theoretical concept of what we or how we can describe the value of a machine learning model. And our aim as researchers is to maximize this value. So anyone wanting to use our proposal in practice, any practitioners could assess this value and rate the quality of our model so it can be used in practice. So the pragmatic assessment, as the authors presented it, that we can think about the pragmatic assessment as the what should research and machine learning in cybersecurity or network intrusion detection do to allow practitioners to estimate the real value of proposed solution. Yeah, so we want to help them to estimate the real value. Um, because the practitioners wouldn't implement or reproduce the method if the value or the information is not clear within the paper. Yeah, so we want to help them, and this is the practical assessment proposed by the authors, which focuses on requirements for developing the machine learning method. So we need to clearly specify them. We need to evaluate within test environments or the test beds which resemble operational scenarios. And we want to make sure or want to maximize the chances that our results will be free of experimental bias and have a high degree of confidence. So this is basically it. As I was discussing on the previous slide, the pragmatic assessment is reporting of unbiased performance in the likely operational scenarios and to provide requirements of the machine learning method. So this is the pragmatic assessment, and we will go through these steps now one by one quickly. So the pragmatic assessment part one, we want to report the development requirements. So in our papers, in our work as researchers, we want to disclose all the information uh, of developing and maintaining a given solution. So yeah, we need to disclose S, which is the system, the full system, the infrastructure, with the respect of the proposed machine learning solution. So what model do we use? What are the components, specifics, post-processing we use, and so on and so on. We should disclose hardware specifications, so what platform was used to train, test, what RAM did we use? Did we use any number of CPUs, GPUs, number of cores, and so on and so on. So this is another thing we should consider reporting in our papers. We should report how our data set is composed. So we increase the value of the data because, as I've told on the previous slide, the data, both labeled and unlabeled, have their value. Uh, why? Because we need to collect the data, we need to label the data, it takes time, it takes human resources, so yeah, data have their value. And if we know how many samples in a data set are there, what are the distributions, how was the data collected, and so on and so on. It helps to determine the cost of a machine learning solution. And then finally, we want to disclose machine learning method details. So what features did we use? What are the exact algorithms and parameters? Did we use binary, multicast classification? What was the pipeline from data collection to the final classification, or even the handling with the classification or the decision data and so on. And if we can, as researchers, we should focus on releasing the implementation of code and data publicly. The second part of pragmatic assessment is reporting likely operational scenarios. So considering our model in scenarios that could occur in reality. So as we were talking, before there is a closed and open world situations, then there is a static and temporal data dependency, and some naive and adaptive attackers. Based on these three steps, we were really, they are kind of intuitive, in my opinion, because we were discussing the common pitfalls in the previous slides, and these three steps are just natural thing to report, to do when we know about the common pitfalls. So let's get to it. We already looked on how the closed and open world situations look like. So just a quick recap. Closed world scenario, the machine learning expects each sample to resemble those seen during the training. So basically giving the model same classes during training than during testing. But this prevents to estimate any form of adaptability. So we cannot tell if how the model would act in practice if the model received completely different type of class, different type of attack, or image, or anything else. Yeah. So we couldn't tell. So these closed world scenarios are very lab or academic. And what we should do, or what we should think about to do, is the open world scenarios to assess the systems assess systems due to the environment unpredictability. So in unsupervised anomaly detection, AD, this is implicit because we learn only normal state and then we detect any anomalies. So this is really implicit and in anomaly detection. But however, in classification problems or supervised learning, how can we introduce the open world scenario? Because what we should do is to evaluate on different classes than or attacks, of course, than those seen during the training. So what we can do is to inject classes which are not included in the original dataset to the evaluation set. So via synthetic sampling or merging from other dataset and so on and so on. But this really can introduce some bias, as we were talking before. And the second option is to exclude malicious classes in the original dataset from being put into the train. So we exclude one class from training and then test with all classes possible. This can even introduce some bias as well, but we cannot really prevent the bias always. So these both approaches are viable and can be combined. And yeah, as we were talking before, combining data from different distributions, different networks should be avoided or done only after precise consideration because it may introduce bias again, which we don't want. Then we were talking about the static or and the temporal dependencies before. So just a very quick recap. There are dependencies in the data, yeah, network data especially, which break the IID principle needed for machine learning. So we need to, or we should evaluate both cases when samples are independent and some dependencies might exist. So we discussed how to prevent these dependencies before, but just very informally, we should choose a test and evaluation set so that the samples come after so the samples that come after train are considered in test and evaluation data sets, of course. And class distributions are similar to the reality. These are some formal considerations. As I said, yeah, time of all evaluation and testing data is higher than the time in training. This discusses our windows, or as I was talking before, we will see in the next slide very briefly, but the time of the window should correspond to all sets or all elements within that window or within the time slot, and of course the realistic ratio of class in testing. So we want to achieve similar class percentage or class ratios in our data than in the reality. There is the window condition I was talking before, but very briefly. And the third part of these likely operational scenarios is considering naive and adaptive adversaries or attackers. Again, we talked about it before, but here is the somewhat more detail of this aspect. So the systems must consider the presence of adversaries. So basically, the idea is to endorse this defensive proactivity by evaluating the machine learning against adaptive attacks that can occur in reality, which is basically the fact that the researchers think about the domain, think about their solution, and what can the attacker do, what are the typical attacks on the similar model, and again, evaluate the model in such a way. So what recommendations are there for a design? Adversaries in practice will do only the profitable attacks or choose low-hanging fruit. So researchers should adapt this adversarial mindset, and yeah, if they want to evaluate their model, they should think about these aspects. So the attackers won't most probably do very complicated attacks, which are costly, but only the simple or the attacks that are profitable. Then consider the right box. The Pitfalls papers discuss that the white box scenarios should be discussed always, but this is not entirely necessary for some domains because usually network intrusion detection, the information about the models is not disclosed to the public, so attackers can only guess or estimate what model that the security solution use and so on. Also, the attacks should be realizable, and uh, real attackers, real adversaries consider unbounded attacks, not only some theoretical ones, which are typically bounded. For example, only one change within the data, but the adversaries will do anything in order to achieve their goal. So they won't have any constraints, maybe only the profit or the realizability of the attack, of course. And the third part of pragmatic assessment is unbiased and statistically validated results. So we should report these statistically validated results by considering the base rate fallacy. We've talked about it before, and we should perform statistical validation, which is really important step in providing a sound results. Why? There is some intrinsic randomness in machine learning and in the sampling as well. So what we want to do is to minimize this bias by statistically validating our results. How to do that? We should repeat the experiments for a sufficient amount of trials while changing our train and test data. So it helps us to establish an unbiased performance of the whole machine learning method. So starting with feature extraction, pre-processing, and evaluation itself, some post-processing, and so on. And when we have large sample of tries or trials, we can use statistical tests or statistical comparisons. For example, t-test, which is important factor to give that can give us a statistically validated result that our model performs in this scenario like this with some deviation because we performed many trials and we see that there are kind of consistent across others. And also, as we talked before, discourage of cross-validation because it introduces temporal bias. So this is the summary. As we talked, pragmatic assessment, reporting unbiased performance in the likely operational scenarios, and provide requirements of the machine learning model. Okay, so this was kind of hard to grasp maybe, but here is some example and some review of the pragmatic assessment again in the state-of-the-art network intrusion detection field, which the authors did. And here we can see if the authors reported hardware requirements. Some of they did, but I think mostly didn't or only partially. Runtime wasn't also considered that often, but interestingly, adaptive adversaries were considered quite often. So this is a nice finding, but statistical significance mostly not performed. Data availability mostly not performed, and yeah, usage of public data was quite popular, and the number of data sets that were used. So this is it. As we can see, even the state of the art does not often provide sufficient amount of information for practitioners to gauge the value of the machine learning solution. And so what are the major findings? No study fits all requirements. Most paper assess the quality of machine learning models on snapshots, so only one evaluation, or do not vary composition of the training set. So yeah, statistical validated results are not very common. They often neglect requirements, so only 10% consider hardware and runtime. But yeah, majority, as I said, considered smart attackers. So this was giving or discussing what the pragmatic assessment is, how the state of the art is in the field, and now is the example from authors of how can the pragmatic assessment be done. You can always see their paper for details and results, but in a very briefly, the authors show that the pragmatic assessment can be done, but with the thousands of different configurations. As you can see, 5 data sets, 4 data availability settings, so only 100 samples for training per each class. As an example, 2 variants of feature set, six different machine learning pipelines, yeah, binary, multi-class, some cascading, ensembles, and so on, 4 different algorithms, and 6 different hardware. So yeah, this gives us thousands of different configurations. Of course, performing the pragmatic assessment as the authors designed it is not super comfortable and super super great in practice because it is really time demanding. Performing so many trials, varying the data set is not what every research can do, but the authors suggested to do some practical recommendations that every research can adopt with very little changes and very little extra time needed. So pragmatic assessment, as we presented it before, let's call it just for elite papers or researchers who have a lot of time. But we, as regular researchers who want to provide and research interesting methods available or for practice or good for practice, we should find some sweet spots or some feasibility of doing the experiments the pragmatic assessment uh, mm, gave us. So what we can do, we should focus on statistical significance and repetitions. This is very important because only one data set, only one train test split gives us very little information about how the model will perform in practice. But statistical significant results are very expensive and tedious to achieve. So we would need to do many trials to split the data into many subsets or use completely different data sets. But yeah, many trials, which is problematic. And we cannot often manage to do that many. So the authors recommend to change train and evaluation set at least X times, which is 3 to 3. So change train set 3 times, evaluation set also 3 times, when we have sufficient amount of data. When we have scarce data, so only less than 100,000 samples, for instance, at least do 10 by 10. So vary the data, vary the compositions, try to perform at least several trials. So we can see that the achieved results are not coincidence, were not random, but were achieved with some significance or with some um, way to tell that the results are correct. Yeah. And the practical recommendations number 2, give experimental details in your method. So provide details of a test bed in our papers. Only issue is we have page limitations. So provide link to supplementary files or to appendix, but in order to make our research replicable in practice, we need to provide experimental details. We also need to report performance, so use at least 2 classification metrics for detecting intrusions or malware, usually true positive rates, false positive rates, but of course, more metrics, the better. Measuring runtime, we discussed that. We should vary the test bed, at least the training data, the amount of training data. So we should reduce the amount of data in our training classes to see how the model can learn, how the model performs when the limited amount of data are given. And of course, we should know our data and model decisions by analyzing data, analyzing model decisions, and explaining them in our papers. These are practical recommendations we can implement to our papers from the pragmatic assessment. And that brings us to the end. So, what are the conclusions of this, I think, exhausting talk? Many things can go wrong during machine learning, not only evaluation, but the whole machine learning process, from collecting the data to training the model to evaluating the model to deploying the model into the practice. So when we know mistakes which are common or which are even uncommon, the better we can avoid them, the best for us. We should know our domain and data. How so? Can a temporal bias be introduced? We should tell by the data we work with. What is the common distribution of certain class or certain classes in reality? So if we know what is the distribution or some approximate at least, we could form our data set to have an approximately same distribution as the reality. Again, knowing our data, are there any features that can cause spurious correlations? Yeah, timestamps, IP addresses, MAC addresses, whatever, our file names, DNS, I don't know. Depends on your domain, depends on your data, depends on what are you doing. And when we are evaluating our model, try to make it useful. So pragmatic assessment is not necessity for every research that has to come in the future. Even the authors of the paper said that. But we can try to pick up some best practices as we've given you there and implement them into your research. Yeah, reporting hardware, reporting runtimes, varying data, and so on, doing multiple trials. Try to make our evaluations useful. And so that's it. If you were interested in some more pitfalls, I found this paper on arXiv, which discusses a superset of what we discussed today. Then there are references are used. I used for this talk. We discussed mostly these three papers from Pendlebury, from ARP about the 10 most common pitfalls, and the pragmatic assessment was given here by Apruzzese. So that's it. If you will have anything more to discuss, feel free to give a comment under the video, write me an email, or whatever you do, do it with happiness and enjoyment. Thank you for being there. I wish you a pleasant day and good luck in your machine learning research and projects. Goodbye.